in the lecture on discrete models. So the thing is to optimize functions where the variables that you are touching, they are integers, they are discrete binary numbers, and we will see different approaches. So these models, in general, they are very much tailored to the specific problem you are talking about. So we will see, for instance, for the knapsack problem. The knapsack problem, I remind you, it was this one. See, this one. So we are given a set of objects. Each object has some value. So the value is expressed as value per kilogram. They have some weight. And then you want to maximize the total value subject to the capacity of your knapsack. And the variables that you can control are 0 or 1. So whether you take this object into the knapsack or not. So this is a problem we want to solve. And we will use that problem to introduce a new technique, that is this dynamic programming. So dynamic programming, somehow in general, if you want to think of it, is like I have to solve a complicated problem, and then I try to solve a problem that is simpler. And by moving kind of in time or something like that. So let's say that you have already filled your knapsack, and except for a small region. So you have your knapsack, you have already chosen some elements. So let's say that you have chosen element 1, and then you are deciding what is the next element you want to put. So the next element, once you are given that you have already chosen 1, it is a little bit simpler, because now before you had 5 elements to solve, and now you have only 4. And the idea is like that. So let's move a little bit further, so that each problem, as we get closer and closer to the end of the solution, it is much simpler. So let's say that you have chosen 1 and 3, and then what is the next element, and then you decide I cannot take any other element. Okay, so you move by adding or by trying to get closer to the end. That is the general idea of dynamic programming. So let's see dynamic programming in this particular case. And in this particular case, so let's formulate first the problem. So we want to maximize the total value, that is this thing. So the value times the whether we take the element or not, subject to the capacity. And let us assume that the weights are integers, otherwise we cannot use dynamic programming. So we will construct a table. So let's say that we have n elements to take. So we have n possible objects to put into the knapsack, and we will construct a table that has n rows, or it goes from 0 to n, so it has n plus 1 rows. And we put in columns, we put all the possible weights, and we initialize it to 0. And the meaning of an entry here in this table is the maximum total value achievable using the first I items with a knapsack of capacity W. So you see the I row and W column represents this thing. So using the first I items, and given this capacity that goes from 0 to the total capacity, what is the best maximum total value that I can get? Okay, so, and for the moment, it will be 0. And then we will fill it in this way. So we will, if item I is not taken, then we simply copy the previous row at the same weight. And if Wi is smaller than W, then we take this thing. So it is the maximum between the previous value or so the previous value in the previous row, or the new value plus the value in the previous row once we subtract this thing. So we subtract the current weight from the current capacity. And like that, you can fill this table. Okay, so let's say that these are our items. This is the value of each one of the items and the weight. And we have a total capacity of 15. So we start with all the rows at 0. Okay. Then we take, so item 0 is not here. Okay, so item 0 is no item. So now we take item 1. And with item 1, the weight is 4. So for the capacity 0, 1, 2, and 3, well, we cannot take it. So we cannot take it. So the value up to there is 0. And then at value, at weight 4, we can take it. And then all the, if we just use items 0 and 1, 0 is no item. So items 0 and 1, with all these capacities, this is our maximum value. Do you agree with that? Okay, so this is obtained, we have reasoned it, but if you apply this formula and carefully go from I1 and carefully apply this one for all the entries in the table, you will get these values. Okay, now let's say that you are allowed to take items 0, 1, and 2. So it is this row. Then item 2 has a weight 6. This one has a weight 4. So at a capacity of 10, you can take item 2. Okay, and then up to capacity 9, you are only able to take item 1. And then at capacity 10, you are able to take item 2. And this is given by this formula here. Okay? So it is simply applying the formula for all the items, for all the entries there. Okay, so we construct a full table, and then we explore with this capacity, what is the maximum value I can take? So the maximum value I can take is 53. Okay, how did I get this 53? So either you keep a track of how you got to this element. So this element was obtained by, you had item 0, so capacity 0. So then with item 3, you got a value of 20, and the weight was 5. And then item 4 added a value of 15, and the weight was 3. So you jumped from 5 to 8. And then with item 5, you added 18 of value, and the weight was 7. So it is 8 plus 7, you go to 50 here and 53. So either you keep track how you got to this cell, or you try to reason it back somehow. Okay, so these are the changes we have made. So this was coming from this one, and this was coming from this one. So you see here this comment that I did at the beginning. So we try. So once you are given all these capacities, and all these values with item 4, getting what is the value of this one, of item 5, for each one of the capacities, it is trivial. It is very easy to do that. Okay, so if you are given all the capacities and all these rows, okay, so this is just very close to the end. So we have already solved the problem for all the items, and then you can very easily get what is the value of item 5. So you see, you get to the end, and then you try, or almost to the end, and then you try just to add item 5. and that is relatively easy. And then you go to item 4 and 3 and so on. And here you have the formula. Here you have the code, the Python code to do that. Any question up to here? No? So this is dynamic programming as applied to knapsack. So the general concept of dynamic programming is trying to solve a problem, assuming that you have solved the I-1 problem. So try to solve the problem at I, assuming that you have solved it for I-1. Okay, so a different family of algorithms, these greedy algorithms. So a greedy algorithm builds a solution step by step by repeatedly choosing the best local option available at that moment, without considering previous decisions. So at each stage, you try to get the maximum value from your current choice. And that is why it's called greedy. And yeah, there are some problems in which greedy is relatively good. So this activity selection, so peak, so you have to organize a set of activities and each one has a different timing to finish. So which activity should I choose first? And the first one, according to this, so I want to maximize the number of activities that are executed. So pick the one with the smallest finishing time. And then if you keep that strategy all the time, then you are guaranteed to get to the optimum. And then Huffman coding. So Huffman coding, have you seen Huffman coding? No? So it is a way of compressing data. So you have a set of symbols to transmit or to encode, and which is the least amount of bits that I need to encode those symbols. And then it is this Huffman coding. The greedy strategy there is to combine the least frequent symbols first. So you combine them as if they are a single symbol, and then you keep doing that strategy, and for each one of the symbols you repeat this process until you are given only 2 symbols, and then you assign 0 to one of them, 1 to the other. Yeah, so there are a number of problems for which the greedy strategy gives you the optimal solution, but there are some problems for which it doesn't, and the 0-1 knapsack is one of them. So it is one of the 0-1 is either I take the object or not. So it is one of the problems for which being greedy is not so good. And here you have a few of those problems. So 0-1 knapsack, shortest path with negative weights, and general set cover. So you have a set, you want to cover it with a partition, and then the greedy is not the best solution always. No, not the optimal solution. And here we would have an example of it. So let's say that we are given the same items as before, so the values and the weights are the same. So we will compute what is the value per weight unit. So this is the most valuable object, is number 4, because for 3 units of weight, you get a value of 15. So the ratio is 5, so it is the most expensive item. So if you are greedy, then you would choose what is the most valuable item here. So the most valuable item is 4. So I will take it. And now I have a value of 15 and a weight of 3. And then what is the second most valuable? So it is 3. So then I have a value of 35. That is the sum of these 2 objects. And then this weight. And then the next most valuable is this one. And then my weight is 12. And the remaining objects, number 2 and number 5, they are weightier, they're heavier than my capacity, so I cannot take them. So the total value is 47, which is not bad. I have almost used my whole capacity, but I don't get the maximum value and I don't fully occupy my capacity. So you see, being greedy, it is very simple, very, very easy to apply, but it doesn't guarantee that you will get the best solution, as we said here. But it is very easy. It is much easier than this thing here. So this thing is complicated, although it goes to the optimal solution. This one gives you a reasonable solution, but not necessarily the best. Okay, then different kind of algorithms. So we are seeing different families to solve these discrete models. So these hill climbing algorithms. So it is again an iterative algorithm that starts with an initial solution, and then you make small changes to the solution. If the new solution is better, then you take it and you iterate until there is no further improvement. And it is called hill climbing because it seems as you are taking better and better solutions all the time, it is like stepping uphill. So it is like climbing a mountain. Okay, so there are some variants to this. So the simple hill climbing is evaluating the neighbors one by one and pick the first improvement. So I have the list of neighbors I want to evaluate, and I start evaluating one by one. And the first time I find something that improves my current solution, I take it, and then I start again by computing new neighbors. So we will see an example. You will get it better. So another variant of this is, okay, I will evaluate all the neighbors and then pick the best, the one that is giving me the largest improvement. So that is the steepest ascent hill climbing. Then stochastic hill climbing, that is randomly selecting one that is improving my current solution. And random restart, that is repeat hill climbing from random starting points to escape local optimum. Okay, so let's see this hill climbing applied to this method. So let's say that my initial solution is at random. So I start from this random solution that is taking items 2 and 4. The value there for items 2 and 4 is 25, and the weight is 9. And here are the items. And then I compute one of the neighbors. So one of the neighbors is this one. So you see all the beats are the same except this one. So it is a neighbor. So this solution is a neighbor of this one. And the value is 45, which is better than 25. And the weight is 14, and these are my items. And now I compute a new neighbor. So a new neighbor is this one. So let's say that my solution is, this solution is not so good. So you evaluate all the neighbors, and I'm showing you one of them. So this is not so good. So I will discard this neighbor, and then you evaluate all the other neighbors. None of them is better, so you stay there. So this is your solution, and this is your solution because you started with this one, which is random. Okay, so now let's say that I start from this solution that again it is random, and the weight of this solution is 16, so it is infeasible, and the value of an infeasible solution is 0. Okay, I compute one of the neighbors. So one of the neighbors is this one, that is simply changing the speed. And then the value is 33, the weight is 10, and another neighbor is this one, the value is 53, the weight is 15. So I take this one as my current best solution. I compute another neighbor, so this neighbor is not improving, so I don't update my solution. And then you keep exploring all the other neighbors, none of them is improving, and then this is your final solution. So I think it's relatively simple algorithm too. But you see that it depends a lot on the initialization. So now you understand better this random restart. So you start from random places and try to get to the local optimum. Any question at the end? No? Okay, another algorithm is this taboo search. So taboo search, again, it is an iterative algorithm that explores the solution space by moving from a current solution to a neighbor, so a little bit like hill climbing. And even if the move temporarily worsens the objective function, so you may take movements that are worse at some moment, and you maintain a taboo list to prevent cycling back. Okay, so I think it is better understood with an example. We will see later. So there are a number of components of this algorithm. So you have the solution space, that is all the set of all possible solutions. You are currently at some solution, like one of these ones. Okay, and then you can compute the neighborhood of that solution. So which ones are different simply by one variable. So like we did here. So this is a neighbor of this one. And if I compute 1, 1, 0, 1, 0, it is also a neighbor of this one. Okay, so you compute all the neighbors. And you need an objective function to minimize or maximize. You will have a taboo list. So this taboo list keeps a track of the movements of the states that you cannot take in a number of iterations. So for the next 3 iterations, I cannot take these 3 solutions. And that is the goal of that list is to prevent the system from going back. So let's say that you decide to move from this solution to this one. You decide to do that. And then this element is in the taboo list because you don't want this one to go back to the original one, because you would be all the time going from first to second, second to first, first to second, second to first, and you want to prevent those cycles. So you say for the next 3 iterations, you cannot take this solution. We will see an example. Okay, and then you have an aspiration criterion that is it allows overriding the taboo status if a move leads to a solution that is better than any one seen so far. So even if you are in the taboo list, if the solution that you are proposing is better than anything seen so far, you are allowed to take it. And then some stopping criteria, so maximum number of iterations, maximum execution time, no improvement over the last, I don't know, 100 iterations or whatever. So there you have a pseudocode of that thing, of that algorithm. So you start with some solution, you keep a track of what is the best solution, and initially you initialize the taboo list to an empty set, and then you will keep iterating until you meet your stopping criterion. And then what you do is you generate the neighborhood of your current solution. You remove the moves from the neighborhood to explore, unless so from the neighborhood you remove the ones that are in the taboo list, unless your aspiration condition is satisfied. Then from the remaining ones, you choose the best. So you take the state S prime such that we are minimizing here. So we are maximizing, sorry. We are maximizing. Yeah. So even if you are getting worse, you get the best S prime and then update your current state. If S prime is better than the best solution, you update your best solution. So you see that you will keep track of the best solution. And here you're not necessarily bound to get, so if your current solution S is better than S prime, you don't stay at S. You keep exploring the neighborhood. And then you update the taboo list so that you don't go back to S. Okay, and here we have some typical problems where this taboo search is applied. So let's apply it to our knapsack problem. So let's say that we are given this initial solution that is infeasible, so it has 0 value, and then you compute one of the neighbors. So one of the neighbors is this one that has a better value and this weight, and then you keep it, and then you compute a neighbor of this one, that is this one, that has this value and this weight. But you see that you don't stay here, so you keep exploring the neighbors of your current solution. So let's say that I take the neighborhood of this one, and the best one in that neighborhood is this 35. And then you explore the neighbors of this one, the best one is this one, and you keep iterating. At some point, you go back to your best solution. And because you have kept track of what is the best solution seen so far, you don't forget that this was your best solution that you have explored. And here we see the taboo list. So let's say that after the taboo length is, or taboo tenure is 3. So that means that from this solution, you cannot go, the next one cannot be anyone here in the taboo list of the last 3 movements. Okay, and when you move to the next one, the taboo list shifts. So you cannot go from this one, you cannot go to any one of these 3. In that way, you try to prevent these cycles of going first to second, second to first. Any question here? No? Okay, then another algorithm, this one is very much used, this simulated annealing. And it has a very nice property that is one of the few that has a global convergence theorem. So it guarantees that under some conditions, it can get the global optimum. All the others, they were local optimum. But this one guarantees finding the global optimum. So again, it is an iterative algorithm that explores the solution space. So it moves from one solution to another. And they accept worst solution with a probability that decreases over time. So at the beginning of the execution of the algorithm, you are very likely to go from a good solution to a very bad one. But as the execution progresses, this probability goes down. And then at some point, you don't accept this going back to worse solutions so easily. And as the probability goes to 0, then you are guaranteed to find a global optimum. Okay, so let's see how it works. So again, you have a solution space that is the set of possible states that you have here. So all possible states. You have a function to maximize or minimize. You have a neighborhood function. So from this state, which are my accessible states? And then this probability will be controlled by a parameter that is called a temperature. And this temperature and the name of the algorithm, it comes because I try to mimic how materials cool in physics. So let's say that we have a very hot material. So the molecules in that hot material, they are randomly oriented. But then as the heat dissipates, so each system has an energy, and all objects in nature, they try to minimize their energy state. So if it cools sufficiently slowly, then it will have, so if you think of all possible states, so all possible orientations in space, and what is the energy of all of that configuration, then you might have a landscape like this. Okay, so some states, they have less energy than the surroundings, but it is not the global optimum. The global optimum is here. And so you see, every state, so every configuration in space, they have their own energy. And if you cool sufficiently slowly, the system has time to explore the whole global space, and then it will find the global optimum. So that is what it is trying to mimic. And very often, well, dependent on the system, but for instance, for some systems, the final minimum energy state is forming a crystal. So if you give enough time for the system to cool, it will find the crystal configuration. Okay, so that is what we will do. So at the beginning, because the material is so hot, it has a lot of energy available to change from one configuration to the other. So that is the probability of accepting worse solutions. And as the system cools and it goes, the temperature goes to zero, so the system will not have enough energy to jump from a very good solution to something else. Okay, so that idea is something like this. So you are in this point, then you have a lot of energy. You may jump to this configuration. From this configuration, you may jump to this one, which is a little bit worse. From this one, you will, but still you are pretty hot. So from this configuration, you are able to reach this other configuration, which is much worse. And then you are jumping all the time. And at some point, with all these jumps, you will find the global optimum. And then once you are in the global optimum, because the temperature is going down, you will not have enough energy to overcome this energy barrier and then go back to this configuration, for instance. Okay, so this simulated annealing, the process I have explained is physical annealing, so it is how materials cool in nature. So simulated annealing tries to mimic that process. Okay, so this temperature controls what is the probability of accepting a worse solution. So a worse solution is accepted with this probability, that is E to minus the change. So this change is positive if you are going back. So if you are going worse, divided by the temperature. So let's say that the temperature is very, 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 very high. If the temperature is very high, then you're dividing whatever change by a very large number. So that is almost zero. E to zero is 1. So you're almost accepting all the changes at the beginning. But then let's say that the temperature is very low. So when the temperature is very low, then let's say that this change is 5 times the temperature. So this is e to the minus 5, but e to the minus 5 is a low number. Then the probability of accepting a worse solution is a very low probability. Okay, so the algorithm goes like this. So you start at some solution, you keep track of what is the best solution so far, and your temperature is very high. Okay, and then you choose a state that is accessible from your current state. You compute what is the change. So is it the new state? Is it better or worse than mine? If it is better, we are minimizing here. So if it is better, then I keep it. So I always keep better solutions. But if it is worse, I will accept it, with this probability. And we have seen the probability goes to zero as, so if the change, let's say, let's not move the temperature yet. So let's say that my change is very small. So if my change is very small with respect to my current temperature, then it's likely that I take it. Because if the temperature is very small, then this is E to zero, very close to E to zero. And then I will take it. But if the change is very large with respect to my temperature, then I will not take it. Because this is E to -5, E to -10. And then I will not, the likelihood of accepting S prime is very low. And then if it is accepted, then you update your current state. If it is the best solution, then you update your track of what is the best solution, and then you decrease your temperature. So you multiply your temperature by 0.9999. So it will very slowly go to zero. Okay. Any question? Other questions? No? Then we have explained this exponential decrease. So the temperature at the iteration k plus 1 will be the iteration at k multiplied by a relatively a number that is very close to 1. And actually 0.8 would be a very quick cooling. So you prefer very slow coolings. And then there are some other rules. So this logarithmic update. So you start with some temperature, and then you divide by the logarithm of the current iteration. So you are by iteration 1, 2, 3, 4, and so on. Or you decrease by some given amount. So there are different strategies to that. Okay, so if the cooling is sufficiently slow, and sufficiently slow, for instance, this one is one of those, then it is guaranteed that as the number of iterations go to infinity, then you are guaranteed to go to the global optimum. And there is some condition for that. That is that the neighborhood function must allow reaching any state from any other state. So this neighborhood must be such that from a given state, you can reach any other in the landscape. If there are some regions that cannot be explored, then, and the global optimum is there, then you cannot go to the global optimum. And yeah, and this is a reminder of the probability of acceptance of worse movements. It is related. Actually, this formula is also coming from thermodynamics. Have you seen the Wolfram distribution? No, this is it. You don't have thermodynamics. Do you have physics? No? Okay, so it comes from physics. The formula isn't exactly or almost the same in physics. Very good. So let's try the simulated annealing with our problem. So we start with a solution, and then this is the value, and this is the weight, this is the temperature. So we start with a very high temperature, 100,000, and then we compute one neighborhood, one neighbor. So we compute one neighbor, that is this one. It is better. So if it is better, we simply keep it. So we keep this as the next state. Then we compute another neighbor, that is this one. The value is better, so we keep it. And you see that the temperature has started to decrease. And this one is a neighbor of this one. But the value is 0 because it is unfeasible. So if it is infeasible, but still you take it. You take it because the difference, that is 45 to 0, is still at this very high temperature. It is very likely to be taken. And then at some point, you find the global optimum. You keep track always of that. But even if it is the best value that you have seen so far, you jump to another one. You jump to another one that is much worse than this one, but still at this temperature, it is very likely that you take it. You see that as the algorithm progresses, at some point, even if this temperature is still, actually this is not 100,000, it is 100. Okay, so it is a 12.209. So at some point, you don't change anymore. You don't change anymore, and because all the changes in terms of the the gap in the change compared to the temperature, that is what you are computing here, it doesn't allow you. So it gives you a very low probability of acceptance, and then at some point you stay with the global optimum. So this simulated annealing is a very, very good algorithm, very much used. Its problem is that you have to cool the system very, very slowly, and then that takes a lot of time. Any question? Okay, so next family of algorithms are these genetic algorithms. Have you seen them before? Any other thought? No? Again, these are very, very much used, very much. Okay, so it is all these, so not all these algorithms, but you have seen that stochastic algorithms have already appeared a few times. So discrete climbing, it has some stochasticity side. So you may choose one of the improving neighbors at random, and that seems to be good. And here simulated annealing is completely random. So having random things when you are exploring the space of solutions, it seems to be a good thing. Okay, so then this genetic algorithm is another one of these random exploration algorithms. And it is somehow inspired by how populations evolve in nature and how natural selection acts and how the genetic evolution changes the current population, trying to maximize the adaptation to the environment. Okay, so you will have a population, let's say, of n individuals. Each one of these n individuals will have a genotype, so it has a chromosome that somehow encodes the solution. And this encoding typically depends on the problem, but we are in a discrete model setup. So in a discrete model setup, it will be a binary string, so of the kind that we have seen here. Then there is some function to maximize that here in this context, it is called the fitness function. And for every individual in the population, you say how fit, what is the quality of that individual. In our context, would be the value of that individual. And then there are some actions that are intrinsic to genetic algorithms. The first one is selection. So selection somehow tries to mimic this natural selection. So it is a probabilistic choice of the individuals based on the fitness. So the best fitted individuals, they have more chances of staying in the, or somehow being represented in the next generation, while the least fitted, they will tend to disappear, but they don't deterministically disappear. So maybe a very badly fitted individual by chance gets to the next iteration, to the next generation. And then there are some actions on the genetic evolution. The first one is crossover. So the crossover combines parts of two individual parents to create the offspring. So you take two parents and somehow you combine their chromosomes. So somehow you take two parents. So let's say that these two parents, this one and this one that are very good fitted, somehow with these two, you will generate a child of these two. And you hope that if this is well fitted, this is well fitted, the child could be even better fitted. That is your hope. So there is a crossover, also called recombination. There is a mutation. So randomly you change some genes in the individual, and there is some replacement. So the replacement is how the next generation is formed based on the current generation. So how you match parents, and if there is some kind of elitism, so the best individuals in some generation always get to the next one, this kind of stuff. So how you generate the generations based on this one. And here you have some more ideas on how the chromosome looks like. So the chromosome may be just 0 or 1 strings, so sequences of 0 or 1s like we had here, or they can be integers, or they can be real values. So you have a vector of values. And then the pseudocode of this algorithm is the following. So you start with a random population, initialize at random of any individuals, you evaluate the fitness for each one of these individuals, and you iterate for a number of generations until you meet some finishing condition. Typically, it is number of generations. And then you choose two parents from their population based on their fitness. So the best fitted individuals, they tend to reproduce more. You apply crossover to produce offspring. You apply a mutation to offspring. Then you evaluate the fitness of those childs. And then you form a new population from those childs, and possibly the parents. So this possibly the parents. Then, for instance, how to do this crossover? So this crossover here. So you can do a single point crossover. So a single point crossover would be. So let's say. So let's say I have one of the parents is 0, 1, 1, 0, 0. The other one is 1, 1, 0, 0, 1. And then I choose at random one breaking position. I say at random, this one is the same sort here. So you will generate two offspring. So one of them is this part is here, this part is here. So I will have 0, 1, 1, 0, and the one coming from the other part. And then the other will do this. So this part is here, this one is here. So it will be 1, 1, 0, 0, then 0, 0. And this point is at random. Then, so that is called single point crossover. Then you can have a 2-point crossover. So 2-point crossover is, instead of choosing 1 point, you choose 2 points. Choose 2 points. So this and this. And then simply you keep, you swap these 2 groups. So that would be another possibility. The other possibility is this uniform crossover. So for each gene, each one of these elements is called a gene. So you generate one. So for this offspring, you take randomly 0 or 1. For this one, you take randomly 1 or 1. And for this one or zero, and so on. And so those are different strategies for the crossover. And then the mutation example. So the mutation example, so if you have a binary problem, you simply flip one of the bits at random with a given probability, so you can change the probability 0.1, for instance. So you scan the whole genome, the whole chromosome, and then you flip the bits with the probability 0.1. Or the swap mutation, so the swap is you change two bits inside the same vector, the same sequence. Gaussian mutation, so if you have a real value problem, so a problem this kind, where the elements can take any value, you simply add a Gaussian noise, one of the points, one of the components. And then here is some representation of that. So see here how from a parent and two parents, from two parents, how you can generate the offspring. We have also done that in the whiteboard. And then you have a number of individuals, you evaluate them, you choose which are the best ones. The best ones, or you generate crossovers with something that is related to the fitness of these individuals, so that the best fitted individuals they can reproduce more frequently. And then once you have the offspring, you apply a mutation and again evaluate. This is not guaranteed to go to a global optimum, but when the space to explore is sufficiently complex, they can handle pretty well. So there is no guarantee of global optimum, but they do pretty well together. And here you have when this is useful. So when you have combinatorial optimization problems, like the knapsack, the travel salesman problem, things that are non-differentiable, discontinuous problems. So you cannot compute derivatives there of the Hessians and so on. When you have to optimize multiple objectives, and here you have how to go from one generation to the next. So one of the most common ones is this roulette wheel. So select individuals proportionally to fitness. So higher fitness, they have higher chance of being the parents of the next ones. And this tournament is you randomly pick K individuals and then select the best among them. Then this rank based. So instead of ranking better than using the raw fitness for the probabilities of being parents, it is based on, instead of the raw fitness, based on the rank. So the first ones have more probability, but the differences in rank are smaller than the differences in fitness. And then you have this elitism, that is, okay, the best K individuals I will keep from the next generation because they are the best here. I don't want to lose them. This is called elitism. And here you have the example applications. You have population, and then you have the fitness of those individuals, and the average fitness is stable, 90.4. And then you apply this selection for parenting, and then crossover, and then mutations, and then you can see that at some point this 53 appears in iteration 12, so in iteration 12. And you can see also that the average fitness of the population increases, but it stabilizes at some point, and this stabilization has to do with on the average fitness, on the mutation rate. So let's say here we see that not all the population goes to the global optimum. So you have still a few individuals that are not so good. Actually, one of them is stereo. But because of this random mutation characteristic, you can have very bad individuals in one particular generation. But the good ones tend to be overrepresented, and you can always keep track of what was the best of you have seen so far. Okay, any questions? These ones are again very much used. Very. Okay, so let's make a break. The next family of algorithms that we will see of this kind of optimizations is this combinatorial optimization. So combinatorial optimization is a family of algorithms where you want to find the best, the maximum minimum of something from a finite but typically exponential set of discrete structure objects. So the number of combinations grows exponentially. That is the nature, or that is the characteristic of these combinatorial optimization problems. And normally they involve computing subsets of different sizes, or permutations, or matching two sets, or partitioning one set, or things related to graphs. Normally, all the possible combinations, they grow exponentially. They grow with these combinatorial. So the number of permutations, the number of combinations grow very much with the number of nodes, the number of elements that we have to consider. And here you have an example. So let's say that you are given this graph, and this graph, each one of the edges have some value, some cost, and then you want to find what is the subgraph that goes over all nodes with minimum cost. So here I'm just highlighting the cost of the edges selected, but you can imagine you have to compute all possible graphs, subgraphs, or paths in this graph that go over all nodes. That particular problem is called the minimum spanning tree. So it's a tree. So the property, a tree is a particular kind of graph. So it is a tree. It spans the whole graph, and it is the one with minimum weight. Okay, so in general, you will have a finite solution space. So it is finite, but it can be very large, even if it is finite. So it is not infinite, but can be very large. Some objective function, and you want to maximize or minimize that function. Typical problems here, you have the traveling salesman problem. So it is how you should visit all the cities once, and you can explore that through a permutation of cities. So if you consider all the cities that you have to visit, and you put them in order in a list, and then you compute any permutation of that list. So the number of solutions, possible states, it goes with the number of permutations. And the goal is to minimize the true length. So for every permutation, you have an associated true length. We have to explore all of them. The knapsack problem, we have C, the set cover. So you have a set to cover. So you want a partition that covers the whole set. And then how each one of the subsets, each one of the partition is the collection of subsets. So each one of the subsets has some cost or some weight. So you want the one that minimizes the cost, or that minimizes the number of sets. graph coloring. So this is, you want to, you will see that problem. So you will see it better with the figure. Maximum matching, again, you will see it later. So here I'm presenting the problems. I'm not proposing the solution for each one of these solutions. There are specific algorithms belonging to this combinatorial family that explores the possible solutions. The problem is you have a number of cities, and then these cities are represented here by nodes, and then there is an associated cost associated to traveling from all cities to all others. And then you want a path that visits all the cities once and has minimum cost. And then this problem appears in a number of setups. So, for instance, some of them, tracks, deliveries. Okay, this is how it is formulated from the very beginning. But for instance, laboratory pipetting or inspection, they have to visit multiple testing, and so you have a robot that has to explore an area, but that is also a salesman problem. For instance, DNA sequencing, you would never think that this problem could be transferred to DNA, but it is somehow. And there are some variants. So some variants is that there are multiple salesmen, that there is a pickup and delivery time, that you want some cities to be visited before some others, or you don't want to return to the origins, so it's open to. Here you have the graph coloring problem. So you have a graph. You have a graph with some connections. Not everything is connected to everything, you see. And then you want to color this graph with the minimum number of colors, such that not two nodes are have the same color. Okay, so if two nodes are connected, they should have different colors. That is the constraint. How many colors do I need? And okay, that is very nice for colors, but it again appears in many setups. So exam scheduling, so you have to assign exam time slots so that no student has two exams at the same time. So you can formulate that in a graph coloring problem. Or things related to timetables, frequency assignment. So, for instance, the radio towers or distributors to avoid interference with nearby transmitters. That is again a graphical problem. Many things related to scheduling. Then graph matching. So let's say that you have a big graph, you have a sub-graph of it, and then you want to find where this graph is in this one. So let's say that this pattern here is in this area. Okay, so it's there. But how do you find it? I gave you the solution, but otherwise you would have to explore all possible assignments and see if the matching of the two graphs are the same. And all possible assignments, again, is a combinatorial problem. And then you might have different objectives. So, for instance, you may have, you want the topology to be preserved exactly or as closely as possible. So maybe there is some edge here. So let's say that this edge in this graph is not there, but otherwise all the rest, the connectivity is almost the same. So you can look for exact matchings, that is this exact subgraph isomorphism, or approximate matching. Or you may want to have a full graph matching, so the whole, so it is not a part of it, but all the nodes here have to find a match in all the nodes there, and vice versa. And this appears in computer vision, in bioinformatics, in cheminformatics, in social networks. So it appears in real-life problems. What is the difference between combinatorial optimization and binary programming or integer programming that we have seen so far? So here, typically, in combinatorial optimization, we are concerned about paths, about sets. Here in integer or binary programming, the variables that we are more focused, they take value 0 or 1, or they take value 0, 1, or 3. So they take some integer value. But it is not so much about paths and sets. Even if you can encode paths and sets as integer value variables. And representation. So typically, they are very much problem specific. So it is not, as we did at the beginning, with you formulate some goal function that is linear, with linear constraints and variables that have to be integer. So typically these things are very much specific to the problems, these problems of graph matching, graph or whatever. So the structure is very much preserved here. And the formulation, so here typically you need specific data structures to represent your problem. And here you use standard mathematics with variables that take integer values or 0, 1 values. There are custom algorithms to each one of these problems. So for each one of these problems I have presented here, there are some algorithms with different properties, and they are specific for the problem at hand. Here you have generic integer programming solvers. And here you may have some constraints that are somehow implicit to the graph. And while here, if you want a particular constraint, you have to fully to be explicit about that constraint. Actually, I think we have here the comparison with the traveling salesman problem, where all these constraints that we mentioned, each city is entered once, and you exit the city exactly once. You could formulate like this if you formulate it in a generic integer programming framework. But if you formulate it like we did here, for example, here, right? Yeah, here. If you formulate it as a permutation, that constraint that you enter into a city once and you exit once, somehow it is implicit in the construction of your vector. So, yeah, integer programming is a general modeling for many combinatorial problems, but not all combinatorial problems are naturally or efficiently expressed as an integer programming problem. So, for instance, these two, the traveling salesman problem and the max flow are combinatorial problems, and traveling salesman can be expressed as this one. But if you want to solve it efficiently, some combinatorial algorithms are better suited to solve this problem. So these kind of problems, they very often have very, very specific algorithms to solve it. For instance, here, let's say that you are given n cities. This n here is 7 cities. So the number of possible pathways, possible paths, it is the combination, so a permutation of those cities, so that is in the order of number of cities factorial. So the factorial grows very quickly, so it can be many. Okay, and then we have the original formulation as an integer programming problem that we presented at the beginning of the lecture. Any question here? So you can compare the integer programming formulation with the permutation-based formulation. So the permutation-based would be You define a tool as a permutation of the cities. So you have a permutation here. And then you want to minimize the distance from going from city I to I plus 1. So I in the permutation I, y plus 1 in the permutation pi, plus going back from the last city to the first one. That is definitely. So you can formulate it like this, you can formulate it like this, and imagine that the methods to solve this problem are different from the methods to solve this one. And all of them would be valid. And then the differences are the efficiency, the number of calculations you have to perform, whether you are guaranteed to get a global optimum or not, things like that. Very good. Good question. Okay, so then in this discrete modeling lecture, we have a different kind of let's call them constraints. So these constraints here in this context, they are called logical constraints. And logical constraints can be if A happens, then B must also happen. So for instance, in the knapsack problem, if you take item 2, you have also to take item 3. They have to go together, for instance. Or at most, one of these can happen, or exactly one option must be selected. And typically you can encode them with binary values and then this kind of conditions, and or not, if, whatever, then whatever, or linear inequalities. So this linear inequalities is solved here. And here we have some examples. So if task A is assigned to Monday, task B must be on Tuesday. Or if item B can be packed only if item A is packed. Otherwise, it doesn't make sense. If warehouse 1 is open, it must serve at least 3 different clients or whatever. So these kind of conditions. Okay, then how do you formulate them? So for instance, you have 2 ways of formulating that. So let's say that you define variables that are binary. So these binary variables you can constrain this way. So if xi is equal 1, then xj is also equal 1. Or if you want to formulate in an integer way, you have to say xi has to be smaller or equal to xj. So these 2 conditions are the same. Or xi or xj, one of the 2 is equal to 1. So you can say xi plus xj larger than 1. So here we have different ways of expressing those conditions and how I can formulate them in inequalities or equalities. So these logical constraints are not a different optimization type. Right? They are constraints that you have, that you may add to the problems you are solving. And yeah, you already so if you have a constraint problem, solving the constraint problem is more difficult than solving the unconstrained one. Okay. Connected to this is this satisfiability problem. So satisfiability problem, somehow it is like, do you remember the feasible region? We used them in the linear programming. So we had a region where all solutions had to lie. So you can think of these satisfiable problems as a feasible region, but in the Boolean space. So let's say that you have 3 variables that can take values 0 or 1, and the solution is valid if this is 1. So is there any combination of x1, x2, x3 such that this is 1? So that is what we want to show. And this can be shown to be an NP complete problem. So you have to explore all possible combinations. This problem is called SAT, that is this satisfiability problem. So SAT is used to solve decision problems with this kind of logical constraints. Somehow in scheduling, in circuit design, the conditions that you have there can be formulated as a SAT problem. And also you can combine SAT conditions with integer programming conditions. So the solution has to be larger than 7. So for instance, here, in job scheduling, so assign the jobs with time slots with no overlaps and dependencies like job A must come before B. It is this variable, if it is this variable is 1, then this variable cannot be 1. So this is the kind of conditions that you can use or you can formulate with this framework. And here you have an example. So let's say that the university needs to schedule exams for certain courses. The rules are no students should have 2 exams at the same time. There are only 3 available time slots. So you either an exam in the morning, at the middle of the day, in the afternoon. And some courses share some students because some students are involved both in 2 courses. Each course must be assigned exactly 1 time slot. So you can formulate that way. So you have the 3 courses, the 3 time slots, and then you have this variable Cj. That is 1 if course C is scheduled at the time slot T. And then you define the variable, this variable, A1 with 2 and 3, that is algebraized in slot 1 or 2 or 3, same for physics, same for chemistry. And then you have all the conditions that we have set. So each course must be scheduled in at least 1 time slot. So it has to be XA1 or XA2 or XA3. So one of them has to be 1, one has to be 2, so that the whole flows is true. The same for physics, the same for chemistry. Each course must be scheduled in at most 1 slot. So it is either not XA1 or not XA2 nor XA1. So you formulate this way. Conflicting courses must not be scheduled at the same time. So if these 2 courses share students, then it must be that either XA is not assigned to the time slot T, or T is not assigned to the time slot T. And this is the same as this one for T equal 1 to 3. So you formulate a set of clauses, and then all together they define kind of feasible Boolean filter. So you may find if there is no combination of these variables, you have here 9 variables. So 9 variables taking values 0, 1. So that is 2 to the 9 solution possible states. So you explore all of them, and you may find that none of them can satisfy these conditions. You may find a few combinations that can satisfy them. Okay, next. Then we have some problems related to networks. So these are networks. Network optimization is also one of the branches of discrete models. So you have a graph, and in this graph you have edges and the nodes that each one may have some values associated. These values can be capacities, can be costs, can be demands. And the graph may be directed or undirected. And the goal is to optimize a function, like, for instance, minimizing the cost of doing something or maximizing the flow from one node to another. So, for instance, let's see one example. So, one example would be, let's say that we are given this graph. In this graph, the number on the right is the capacity of that edge. So, this edge can transport 10 units. This edge can transport 4 units. You want to go from a source to a target. This source, the target is also sometimes called the sink. So you want to transfer as much as you can from the source to the sink. So what is the path that allows me the maximum transfer? So for instance, I have chosen this path. This path is not the maximum actually. So this path is limited by this edge. So the capacity of this edge is 8. So the maximum I can transfer is 8. So I can transfer 8 here. I'm not fully occupying the capacity of the edge. Here I'm fully occupying it, and here again I'm not fully occupying it. So actually this path down here is much better. Path here have a flow of 9. So the thing is, you have to choose all paths between source and sink, and choose the one that allows you to have the maximum flow, the maximum transfer capacity. So this is one of the problems, or you may have cost associated. So minimum cost flow. So find feasible flows that satisfy the demands of each one of the nodes with a minimum total cost, or multi-commodity flows, multiple flows with different sources and sink that share the same network. So you have multiple sources and sinks, but still the transfer capacity is fixed. So how do I share the maximum flow for all the sinks and for all the sources and sinks? Or this circulation with demand, so the flow must satisfy some lower upper bounds on the edges and balance at the nodes. So you can have multiple programs defined this kind of networks. And all this network optimization, again, is a kind of combinatorial problem. Then problems related to paths and tree problems. So finding the shortest path between two nodes. So these, let's say that these weights here, they are the distance between nodes. And then by given any two nodes, what is the shortest path? And here the extract, yeah. So it is one of the most famous algorithms in science. So shortest path between two nodes, all pairs shortest path, and you can have an example about that. K shortest path, so between two nodes. Can you give me the K shortest different paths, or the minimum spanning tree? Minimum spanning tree is a tree that covers all the nodes with minimum cost. And then more problems on networks. So the vehicle routing problem. So you have, for instance, a warehouse. You have to serve a number of nodes here, and then which are the routes that each one. So how do you divide these routes with minimum resources? Then salesman problem. Stated tree problem that is connect a subset of nodes using a minimum cost tree. So it is somehow the generalization of the minimum spanning tree. only to a subset of nodes. Solving most of all these problems in networks, they can be, some, but many can be solved in polynomial time. So it is a max flow or shortest path. So that means that they are very efficient. So as the graph goes, still you can solve it in a reasonable amount of time. While some other problems, they are empty hard. So that means that finding the optimum requires evaluating all the combinations. And if you don't want to, or if you want to find a suitable solution, you may use some heuristics, having some kind of shortcuts that try to limit the exploration space, but they are not guaranteed to get to the global optimum. Typically, they are solved with some of these algorithms, so greedy algorithms, linear programming, simplex, combinatorial augmenting path methods, right? It's combinatorial methods, meta-heuristics. Meta-heuristics is, okay, I will not evaluate all possible solutions because there are so many, but I try to find some rules that cut some parts of the space that are not so promising. And here I'm presenting Discrete, just to illustrate one of those ad hoc algorithms. So this algorithm is the one that, given two nodes, tries to find the best path through these two nodes. So let's say that I am given a node, and then I said, what is the distance from this node to all other nodes? Then we initialize with the distance for all other nodes is infinity, to myself 0. And then you mark all nodes as unvisited, and you create the priority queue. So how I will explore the different nodes. While there are unvisited nodes, then you select the unvisited node U with the smallest tentative distance. So the one that you think will have the smallest distance. And then for each neighbor of U, if going through U gives a shorter path to B, then you update it. That is that way. So if D plus the way between U and B is a smaller than B, then you update D. And then you mark U as visited, so that you will not process it again, and you iterate until all nodes have been visited. Okay, so let's say that you're given this graph, and you want to explore what is the distance between A and all other nodes. So you start with distance that is A to A 0, A to all others is infinity, because we don't know yet. And then in this heap of distances that you will, or nodes that you want to visit, this is so the starting from A, going to A, goes 0. This is the meaning of this. And I want to explore these, start exploring from here. Okay, so in the first step, you take an element from the heap. So now the heap is empty. You explore the neighbors of A. So the neighbors of A are B and D. So the distance to B is the minimum between the current distance, that is infinity, and then going from 0, that is my current pose, plus 1. So the minimum is 1. And the distance to go to D is the same. Opposed for going from A to D is 2. The distance to B is 1, the distance to D is 2. You update the distance vector, and now you include these two nodes in the heap. So, going to B equals 1, going to B equals 2. And this is your heap now. Then you take another element from your heap. Well, I have the first one. So this is the one remaining. The distance, the neighbors to of B are C and D, and then you make the same calculation. So you update C, and going from A to D through B, it takes 3 units, while going diagonally takes 2. So you don't update the distance to D. And then this is your updated distance vector. And then you add this C that was updated. You add it to the heap. And then you pop again. So you pop again. D has no neighbors, because this is a directed graph. This directed graph has no so you cannot escape from D. So there is no changes, and then you escape, you pop C, and again, C cannot go anywhere. So this is your final step. And then you have all the distancing, that is 0, 1, 5, and 2. Or the distance from A to A is 0, from A to B is 1, A to D is 2, from A to C is 5. So this is this. And you see, what is the cost of this? It is mostly the number of nodes. So that is why so polynomial time. So you don't have to evaluate all possible paths in a combinatorial way. Okay, this is all. Any question? So discrete problems in general, they are much more difficult than the linear programming that we saw the first. And very often they have specific algorithms for each one of the problems. And the two most general that we have seen are these simulated today and genetic algorithms. They can solve almost any kind of problem. That's all.